Thank you very much for the invitation. Let's see. So in this lecture, I will be discussing the energy critical wave equation in the focusing case. The interest here stems from the presence of nonlinear objects for the focusing case of the nonlinear wave equation. And the hope is that the results we describe will be a model for what to strive for in other nonlinear dispersive equations with nonlinear objects. So I remind you the nonlinear wave equation is a second derivative in t of u minus the Laplacian of u minus the nonlinearity 1 over 4 over n minus 2 in absolute value times u. And x is in Rn, and t is in an interval I, which for which the origin belongs. And the initial value problem assigns the data u0 at time 0 and the data u1 for the derivative at time 0. Okay. The fact that we have a minus sign in the nonlinearity means that we have a focusing case. That means minus the Laplacian is a positive operator. Well, if the minus, this is a negative operator. So there's a competition between the linear part and the nonlinear part. The fact that we chose the pardon me? Centered on the equator, and that's not me. Okay, so the power of the nonlinearity, this 4 over n minus 2, is such that plus the 1 in the u, we get n plus 2 over n minus 2. And this is the energy critical case. And I'll explain a little bit about that in a minute. And the initial data are in what we will be calling the energy space. The u0 is in the h.1 space, the space of functions with gradient in L2, and u1 is in L2. So in this focusing case, unlike in the defocusing case, there can be finite time blow up, and there can also be solutions that exist for all time, but they don't scatter. And by scattering, roughly speaking, we mean that behave like linear solutions for large time. Now, for the nonlinear wave equation, there is a small data theory, and small data do give unique global in-time solutions which scatter. If you have a large data, you can solve for some time. And then there is a maximal time of existence. And this time of existence depends on the whole function, on the whole pair u0, u1. It doesn't depend just on its norm. And that's the fact that we are in the energy critical space. So why is the energy norm critical? So here criticality has to do with scaling. If we have a solution and we rescale in space and time, and we multiply by 1 over lambda to the n minus 2 over 2, then this is also a solution. And this power is tied to the energy critical power in the nonlinearity and to the fact that under this transformation, the H1 cross L2 norm remains invariant. It's independent of lambda. And that's why we call this energy critical. So if you decide that you want this property for the energy space, and this is the scaling, and then the power in the nonlinearity has to be the one we mentioned. Now this equation has a conserved energy, which I write here. It's 1/2 grad u0 squared plus u1 squared minus n minus 2 over 2n, u0 to the power 2n over n minus 2. And notice that the energy can be both positive and negative. It is easy for this equation to construct solutions that blow up in finite time, let's say at time equals 1, by considering the ODE associated. We just ignore the sorry. We just ignore the space dependence and just solve the ODE. And this turns out to be, when n equals to 3, it turns out to be a solution which clearly ceases to exist at time 1. Now, of course, this is not a solution that arises from data in the energy space, but using finite speed of propagation, we can truncate the initial data at time 0 and construct and then have solutions which at time 1 blow up by having the H1 cross L2 norm become infinite. We will call this type of blow up type 1 or ODE blow up. There's also what we call type 2 blow up, and those are solutions which cease to exist at some finite time, but whose norm remains bounded up to the final time. And the blow up happens by concentration. In this case, the gradient squared of the solution is going to a delta mass. And this type of concentration is typical of the focusing energy critical problems. Examples where this happens have been constructed. The three-dimensional case was the first examples were due to Krieger, Slag, and Tataru. In the four-dimensional case, there's an example of examples of Hilaire and Raphael. In the five-dimensional case of Gendridge, and there are other examples too. So we will study solutions that remain bounded in the energy space. So we will not touch the type 1 ODE blow up. So we will require our solutions to remain bounded up to their last time of existence, which could be infinite. So let me give some examples of bounded solutions where the final time is infinite. The first example are scattering solutions. A scattering solution is a solution such that when you subtract a linear solution with some other initial data, as time goes to plus infinity, the difference goes to 0. So that means that the dynamics of this nonlinear solution equals the dynamics of this linear solution. And that's what we mean by scattering. And in the defocusing case, it was proved in the late 90s and beginning 2000s that given any data, no matter what its size, the solution exists for all times and scatters. So this is the summary of about 15 years of research. Okay, so don't take it lightly. Okay, so we are concentrating on the focusing case, and this is where the nonlinear objects appear. The first examples come where in the equation we forget about the t dependence and look at solutions that depend only on x. We call them stationary solutions because they don't depend on time. And any solution of this nonlinear elliptic equation, let's say not identically 0 because the 0 solution is not interesting, is a solution also of the nonlinear wave equation. This nonlinear elliptic equation has been studied extensively, especially in the 80s in connection with the Yamabe problem in differential geometry. The first solution for this nonlinear elliptic equation is W of x, which has an explicit formula here. And we notice that these stationary solutions do not scatter because for a scattering solution, when you confine them in space, the energy norm does go to 0 as you tend to infinity, because this happens for the linear solutions. And For a static solution, this cannot happen because this is independent of time. So, okay, as long as it's non-zero, this quantity will not be zero. This W has interesting characterizations. It's a very well-studied object. Up to sign and scaling, the scaling, of course, is the same one that we saw before. These are the only non-radial, non-zero stationary solutions. So plus and minus W lambda are the only radial, non-zero stationary solutions. Again, this is the result of extensive work in the theory of elliptic equations in the 80s. The other characterization of W is that up to translation and scaling, it's the only non-negative solution. Okay, this follows from work of Nirenberg and others. W is called the ground state because it has a variational characterization minimizing the energy. If you consider the energy and you minimize it among all non-zero solutions, you do get a minimum, and it's attained at plus and minus W and its rescalings and its translates. Because of this, it is called the ground state. Now, there are many other solutions of the elliptic problem have been found by many people. I mean, the first instance was a work of Ding, but there's an abundance of variable sign stationary solutions, and they have not been categorized or classified. And they are not discrete, they don't quantize in any way. The only thing that does happen is that there's a gap between the energy of W and the next level of energy. There's a definite gap there. Other non-scattering solutions are the traveling waves. So how does one obtain a traveling wave solution? So a traveling wave is a solution that remains constant in a certain direction. Okay? So one way to produce traveling wave solutions is by using a Lorentz transformation to stationary solutions. The Lorentz transformations leave this set of solutions of the energy critical nonlinear wave equation invariant. And so this is another invariance of the problem, and we can apply Lorentz transformations to stationary solutions. And so for that, we pick a vector of length less than 1. 1 here is the speed of light. So in this model, and so these are subliminal speeds, subluminal speeds. And the traveling wave solution that you obtain is given by this horrible formula in terms of the L. But it is a traveling wave as it's exhibited here. It travels in the direction of L. For any direction whose length is less than 1, there is any solution of the nonlinear elliptic equation, there is a traveling wave solution to the nonlinear wave equation. But of course, if we restrict our case to the radial case, this destroys radiality as soon as L is non-zero. So in the radial case, L has to be 0, and we only have static solutions, plus and minus W lambda. In general, with Duyckaerts and Merle, we proved in 2014 that all traveling wave solutions to the nonlinear energy critical wave equation are given by Lorentz transformations of static solutions. Okay, so this is the list of the traveling waves, and it's a huge list. So what I'm interested here is the behavior of solutions of the nonlinear wave equation for large solutions. So large solutions, large time. And the study of these in the focusing case, oh, so by the way, in the defocusing case, there's no traveling wave solutions and there are no static solutions. And these are our nonlinear objects here, and they don't exist in the defocusing case. So at the beginning of the study of the long time large solution behavior, I started with a paper that appeared in 2008 that I wrote with Frank Merle. And the result is the following. Suppose we restrict ourselves to studying solutions of the nonlinear wave equation whose energy is strictly smaller than the energy of W. In that case, if the L2 norm of the initial data U0 is smaller than the L2 norm of W, the solution exists for all time, both positive and negative in time, and scatters in both time directions. In the case when it is bigger, then it has to cease to exist in finite time. It's blow up in finite time in both time directions. And the third case, the case of equality, is impossible because of this constraint. So variational constraints, considerations show that this constraint eliminates this possibility. Now, soon after, the threshold case, when the energy equals the energy of W, was completely described by Duyckaerts and Merle, soon after my work with Merle. So the thing that we're interested in is the case when the energy is bigger than the energy of W. So this is the case where we're concentrating now. When with Merle in around 2005, we introduced our concentration compactness rigidity theorem method, which is used in the proof of the result I just mentioned. The ultimate goal was to describe the asymptotic behavior of bounded in energy solutions as t tends to the finite time, whether the finite time is finite or infinite, in the spirit of the soliton resolution conjecture. So let me do a brief detour into the soliton resolution conjecture. So since the 1970s, there has been a widely held belief that what are called coherent structures and free radiation describe the long-time asymptotics of solutions to nonlinear dispersive equations. So this belief came to be known as the soliton resolution conjecture. So properly speaking, this is not a conjecture, it is a belief. It becomes a conjecture when you specialize it to concrete situations. So roughly speaking, this belief says that asymptotically in time, the evolution, which could be extremely complicated, but eventually it simplifies and it decouples as a sum of modulated traveling waves and a free radiation term. And by that we mean a dispersive term solving the associated linear equation. Okay? So the origin of this statement goes back, it has a very interesting beginning, goes back to this puzzling paradox in a numerical simulation of Fermi Pasta Ulam at Los Alamos, which was the first numerical simulation of a partial differential equation. And so this is the birth of scientific computation. And this was done soon after the war ended. They had a nice machine at Los Alamos, which they used for the computations related to the nuclear bomb. And Fermi decided that a good use for this machine was to do scientific computation, and he was right. This was a good use for computers, and then a paradox arose out of this numerical simulation. Fermi died soon after, and it remained unresolved for many years. In the mid-1960s, in order to explain the Fermi-Pasta-Ulam paradox, Martin Kruskal brought the convective rays into the equation and the fact that it has traveling wave solutions. And the fact that there's a connection between the Fermi-Pastor-Ulam experiment and the correct de Vries equation, and that the correct de Vries equation has traveling wave solutions, they call them solitons at that point, explained the Fermi-Pastor-Ulam paradox. And this led to another numerical simulation by Kruskel and Zabusky, which was very influential. And this simulation was on the correct de Vries equation. And so in a simplified way, what they discovered were two remarkable things. The first is that if you want to solve the correct de Vries equation with data which are concentrated in one mode, in one Fourier mode, then the evolution for large time was just the sum of traveling waves, at least numerically. And the second thing that they observed numerically is that if you start with two traveling waves and you evolve by the correct de Vries equation, the two traveling waves will collide. They'll hit each other. But after the collision, they reappear unchanged, except for translation. And they call this an elastic collision, because they collide as if the equation, they reemerge as if the equation was a linear equation instead of a nonlinear equation. And this was a very interesting observation. So the first experiment was performed in connection with explaining the Fermi-Pastor-Ulam paradox. And it directly gave rise to the soliton resolution conjecture. The second experiment was eventually seen as a consequence of the concept of integrability, which became an important new concept in nonlinear science that emerged from this. So this two numerical experiments of Fermi-Pastor-Ulam and then Kruskel and Zabusky led to a lot of important consequences. Now, soliton resolution has been proved for a few integrable equations. Now, integrable equations are nonlinear equations that can be reduced to solving a collection of linear problems. They're very important because they do appear in very important nonlinear phenomena, but they are not, this is not a generic phenomenon. Nevertheless, the proofs in the integrable case are still very challenging, and there's issues that have not been resolved yet, even in the integrable cases. There are many, many results also in perturbative regimes, let's say near a traveling wave solution for many different problems. Now, this phenomena of soliton resolution has also been observed numerically and experimentally in many settings. And what one observes this mechanism for relaxation to a coherent structure is the radiation of excess energy to spatial infinity. That's how the solution becomes decomposed into these traveling waves. Now, this kind of phenomena has been observed in many diverse settings. For example, you can see it in a lab in the dynamics of gas bubbles in compressible fluids. And you can see it numerically, experimentally, in numerical experiments in the formation of black holes in gravitational collapse. You can also see it, for example, in the vorticity formulation of the Euler equation in 2 dimensions. So that's another setting, an incompressible setting, where you can see this. Now, proving that this soliton resolution conjecture holds in generality for non-integrable Hamiltonian models is a major goal in the study of nonlinear dispersive equations. So let me now turn to the asymptotic simplification results for the nonlinear wave equation. The first result in this direction we obtained with Duyckaerts and Merle in 2013. And the theorem says that suppose we have a radial solution of the nonlinear wave equation that exists for all positive time. So t plus is plus infinity. Then there is a number j and a radial solution of the linear wave equation, the radiation term, and signs ij, which are either plus or minus 1, scaling parameters lambda sub j, and we can order the scaling parameters like this. And this double inequality sign means that the ratio of lambda j minus 1 over lambda j tends to infinity as t tends to infinity. So the different scalings decouple, but they're also all much smaller than the self-similar rate given by t, which is the opening of the light cone. Okay. So we get these parameters, and the result is that the solution then equals the sum of the rescaled solitary waves, which in this case are static because we're in the radial case and we're in 3 dimensions. So we have the sign, we have the rescaled ground state, then we have the radiation term, and then an error that goes to 0 in the energy space. Okay, and then the corresponding result for the time derivative, the w's don't depend on t, so they don't appear here. It's just the radiation term, plus a term that goes to 0 in L2. And there's corresponding results for finite time. Okay. So let me explain the key ingredient in the proof of this result. The key ingredient is the following fact. Suppose we have a radial solution of the nonlinear wave equation in 3 dimensions, and suppose that it's defined for all time. And this is not essential, but it makes the formulation of the property the cleanest. And suppose that it's not one of the known solutions, let's say. It's not 0, and it's not plus or minus w sub lambda, okay? So these are the 3 known solutions. If you eliminate those 3 solutions, then an energy channel forms. So that means that there is a number r, and there's a number eta, such that either for t bigger than or equal to 0, or for t less than or equal to 0, when we look at the energy outside of this expanded light cone starting at r, there's always energy for all times going to infinity, either for all positive times or for all negative times. And this, of course, fails for the 0 solution. Okay, that's not hard to see, but it really fails also for w lambda. It's independent of t, and so when you take t large, this quantity will go to 0. Okay, and this is a way in which you quantify this radiation of excess energy to spatial infinity, which is seen in these experiments that I mentioned before. Because at spatial infinity, there's always some energy. Okay. The proof of this fact relies on what we call energy channel lower bounds. Okay. So let me explain what those are. So we start with the 3-dimensional n equals to 3. We fix a number little r naught, and we look at a over r comma 0 as a subspace of h1 cross L2 of r bigger than r naught. So this is a 1-dimensional subspace. And here, 1 over r, we're in 3 dimensions, 1 is n minus 2. So this is the Newtonian potential. And this is the subspace generated by the Newtonian potential. So this is the radial functions in H1 cross L2. And now we look at the orthogonal projection to the orthogonal complement of this one-dimensional subspace. Then for any radial solution of the linear wave equation, either for t bigger than or equal to 0 or t less than or equal to 0, there's energy outside. And the constant here is 1/2, provided you stay away from this one-dimensional family. This one-dimensional family is a counterexample to this inequality because it's easy to see that the solution corresponding to this in this set would be A over R, and this would go to 0. So provided we project away from this one subspace, we have this. And this is true for all R0. The proof of this is elementary. So I just say that it can be done in one page. And it uses only calculus. Okay. Here, the key point, the connection to the nonlinear problem, comes from the fact that the behavior at infinity of the ground state is the one of the Newtonian potential. And this is what appears in this exceptional subspace. This inequality easily gives this one for the linear case. But to go to the nonlinear case, you have to use, I'll get to what you have to use later on. But let me continue by saying that this inequality too has an analog which is non-radial. And it holds in Rn cross R for all odd dimensions. We proved that with Duyckaerts and Merle around 2011. And this says that for all t positive or for all t negative, there's always energy outside the light cone. So there's no R in this inequality. Okay. Now, once you see this three-dimensional theorem, it is natural to ask what happens in the radial case for a dimension higher than 3, and what happens in the non-radial case for all dimensions 3 and higher. And this is what the rest of the story is. That the rest of the story has to be preceded by a few facts that tell you why these two questions are hard. The first fact, which was found in a paper with Raphael Koth and Wilhelm Schlag, is that this outer energy lower bounds have limitations. They fail for all even dimensions, even in the radial case. The second thing is that for all odd dimensions, there's an analog of this inequality that we proved in work with Laurie, Liu, and Schlag. And this inequality looks the same, but the exceptional subspace is much larger. There's many more elements in the exceptional subspace. It's finite dimensional. Here I list them. But as the dimension n goes to infinity, the dimension of the finite dimensional subspace grows to infinity. And already in dimension 5, this has dimension 2. So it's no longer one dimensional. And the third thing is that this outer energy inequalities, where you don't have R0 equal to 0, but you have R0 positive, fail in the non-radial case with a dramatic failing. There's an infinite dimensional failing. Okay? For each spherical harmonic, you can construct infinitely many examples. So it's huge. Okay. The fact that this subspace P sub R naught is of dimension bigger than 1, when n is odd, but the dimension is bigger than or equal to 5, is responsible for the fact that the method of the proof of the theorem 1, which was a 3-dimensional result, cannot be carried out. Now, the reason we can carry out is because we only have to eliminate this one dimension in the 3-dimensional case, and we can use scaling to adjust things to eliminate this one parameter, this one-dimensional space. In higher dimensions, starting from 5, this is not the case, and we don't know what to do with these additional objects that appear from this set of counterexamples to this outer energy inequality. And this has been a really major obstacle until very recently. Okay. Now, the fact that the non-zero solutions of the elliptic equation are such a huge set for which there is no classification, and the fact that all of these outer energy inequalities for R naught positive fail in the non-radial case in a dramatic way means that there's been no analog of theorem 1 in the non-radial case. So these methods did not apply to the non-radial case at this point. So in spite of all this, some weaker results have been obtained by using monotonicity as the time averaging. This is analogous to what people have done for the study of geometric flow problems of parabolic nature, for example. The results that you can obtain, though, in this way, instead of holding for all times, hold for well-chosen sequences of times. So the first result is this theorem 2 that says that if we look at bounded solutions that exist for all time of the nonlinear wave equation for n bigger than 3, then this decomposition holds, but only along a well-chosen sequence of times t7. The second result, the case of n odd was done by Casey Rodriguez, and the case n equals 4 we did with Cott, Laurie, and Schlag, and the case of all even dimensions with Hao-Jia. Okay, so there was some restriction in the range, but it's a technical restriction, so I'll ignore that. The theorem 3 proves an analogous result in the non-radial case. So suppose U is a non-radial solution of the nonlinear wave equation in Rn for n between 3 and 6, and as I said earlier, this is a technical constraint, which is bounded in the energy. Then we can find the radiation term, a linear solution, a well-chosen sequence of times, scaling parameters, lambda jn, centers xjn. The centers remain well within the light cone. When you rescale the centers by the scalings, you obtain directions Lj, which are also within the light cone because the lambda jn's are much smaller than t sub n. And these are the directions that we get. And we find also traveling wave solutions, that is to say, solutions of the nonlinear elliptic equation and their Lorentz transform along these directions Lj in such a way that the difference between the nonlinear solution and the linear solution is the sum of the modulated solitons, and the same for the time derivatives. And this different solitary waves are well separated by their parameters because either the ratios of the scalings or the separation of the centers up to the scalings must go to infinity. So these are traveling waves that don't see each other. Now, the remark that I want to make at this point is that a method of proof which uses monotonicity after time averaging cannot give more than a decomposition for well-chosen sequences of times. And this can be seen in the example of the harmonic map heat flow into compact manifolds. And Topping showed that if you choose the target in an appropriate way, this decomposition, the analogous decomposition, need not hold for all times. It could be that different decompositions hold for different sequences of times. So for the rest of the talk, I want to discuss recent progress with Duyckaerts and Merle in the radial case for higher dimensions and bigger than 3 and odd. So in a series of 3 papers, which were posted in the archive in December of 2019, we have proved the full decomposition for all odd dimensions in the radial case. So the theorem says that if n is bigger than 3, is odd, use a radial solution, the norm remains bounded, then the full decomposition in the 3-dimensional case also holds in the higher dimensional case. So it is not that the decomposition for well-chosen sequences of times follows from this result. The decomposition for well-chosen sequences of times is the first step in the proof of this theorem. Because of that, by going along this well-chosen sequence of times, we can start in the proof of theorem 2 by studying the dynamics close to a sum of scale static solutions plus a linear dispersive term, because that's what the decomposition for this well-chosen sequence of times gives us eventually. We then understand what happens to the collision of these static solutions, scale static solutions, with scalings that are far apart in ratio. And we show that all such collisions are inelastic, in contrast with the integrable case that was seen by Kruskal and Zabusky. And what we show is that there's always radiation that's produced in collision of static solutions. So let me be specific here. We define a radial solution U of NLW to be a pure multi-soliton, let's say asymptotically as time goes to plus infinity or as time goes to minus infinity, when you have parameters, well-separated scaling parameters, signs, such that our solution for large time looks like this separated solitons. And this lambda j is lambda j of t. Okay. Plus an error that goes to 0 as time goes to infinity, depending on plus or minus as to where you want to go to plus or minus infinity. Suppose that we have U being a multi-soliton as time goes to minus infinity and time goes to plus infinity. Then we say that the solution, that the collision of the solitons is elastic, because this corresponds to saying we have this sum of scale solitons at minus infinity. We start solving, we evolve, and we evolve to infinite time, and then we still have a sum of solitary waves. Now, in the 3-dimensional case, these channels of energy can easily be seen to show that there cannot be elastic collisions. And that's a very simple argument. So in this series of papers, one of our results is that there is a slightly weaker version of this channel of energy property. And it says the following. Suppose we start with a radial solution of the nonlinear wave equation that stays close to a sum of decoupled static solutions for a sufficiently large time. Then, provided you shift up the light cone, or down if you go to negative time, then there's always energy outside for positive time or negative time. And again, it's easy to see that elastic collisions are excluded by this fact. Okay, so let me give some ideas of the proofs of these things. So I'm going to give you a very quick outline of the proof. So in the first step, we have to derive this energy lower bounds, not for solutions of the linear wave equation, but for solutions of the linearized wave equation at the static solution W. So that's the first step, and that's essentially one of the papers is to do this. The next step extends this channel of energy lower bounds from this linearized operator to the linearized operator around a multi-solid. Okay, where the lambda j's are all very far apart from each other. We then introduce the concept of radiative and weakly radiative solutions of the nonlinear wave equation. The radiative ones are the ones that at plus and minus infinity, you do not have any energy outside the light cone. And the weakly radiative ones are the ones that outside the translated cone to R, they don't have any energy either at plus or minus infinity outside. Then the next step, and that's basically the content of the second paper, is that we give asymptotics of this weakly radiative, weakly non-radiative solutions of the nonlinear wave equations in terms of the weakly non-radiative solutions of the linear wave equation. They have the same asymptotic behavior. And this is this finite dimensional subspaces that I flashed before. The proof, the easiest way to write it is by contradiction. We assume that we have the decomposition for some sequence of time, and another one which is close to it, for which we don't have it, but we're close to having it, meaning we miss by an epsilon. We extract the radiation term. This we can do always, even in the non-radial case. This is in a paper of Duyckaerts, Merle, and myself. And then we do a decomposition of the difference between the nonlinear solution and its radiation term. And we do the decomposition into blocks. And these blocks are the nonlinear profiles of Pahuri and Girard. And they are like the building block solutions to the solution of the nonlinear wave equation. Using the fact that they are non-radiative, we are able to find a system of ODEs for the scaling parameters that appear in the decomposition. And we study this finite dimensional system of ODEs And we find the monotonicity formula. A monotonicity formula is finally found, because you cannot solve one of these nonlinear problems in the large for a large time without having monotonicity somewhere. And here it's hidden in the system of the ODEs for the scaling parameters. We combine this with the information coming from the decay of weakly non-radiative solutions, which these building blocks have. And the ones that are not W have a special property. And using this, we obtain, and this monotonicity formula, we obtain an upper bound on the time of existence of this ODE, of solutions of this ODE. But this is a contradiction because our solution existed for all times. And this is the mechanism that we use to eliminate this ghost linear solutions. They do not appear in the nonlinear case. And so that's how the proof concludes. And that's how the talk concludes also. Thank you very much.